Hello, it's Keith here, and this is lesson 5 of the YQuest series of assembly programming tutorials. This time we're going to be looking at the Apple II, the platform-specific code of YQuest for that system. You can see YQuest on screen now. It's looking very big, taking up almost the entire screen. Let's give it a quick go. Now, I decided to just simplify things and use the 2-color mode. In this case, I didn't try and use 4-color graphics because I thought it would be a bit ugly potentially, so I decided to just go nice and simple. So the graphics have been slightly scaled down. They should be 8x8, but they're actually now 7x8, so there's 7 pixels wide and 8 tall. But you can see we basically got the same game. Maybe it feels like it's a little bit slow maybe, but we can very easily tweak that. Anyway though, you can see that essentially we've got the game working here. Right, well, today we're going to be looking at the code that actually made up this game. So let's go over to the source code and let's actually have a look at it all. Okay, so here is the source code for the game engine for the Apple II. Of course, there is some common code that all of the systems share, but we're not going to look at that today. It's just going to be this code we're going to look at. Now, first of all, we're defining the size of the screen here, and this is for the collision detection and things. So this works with the common code, and this allows the game to work on all systems in the same way. We've got some collision detection masks here. Now, because we're limited to 8x8 blocks on most systems and 7x8 blocks technically on this one, we're having to reduce the resolution of the collision detection so that the visual representation of the overlap matches the calculated one. Otherwise it might look like you weren't about to touch an object, but the collision detection, because of the internal coordinates, would think you were and would kill you, which wouldn't be a good thing. So that's why we've got these collision masks here. We're defining some temporary memory here for the working. This simulates Z80 registers, and we've got some user RAM here, which is for the game variables. When the game starts, we're just turning on the screen here, we're just initializing things, and then what we're doing is we're clearing the user RAM. We've then got the setup for the new game here, setting up the lives, the sound and the level number and things, and then we're clearing the screen, and now we're showing the title picture to the screen, which is what you can see just up here. This is this YQuest logo. So we're using the Sprite routine to do this. We're reading in each tile here, checking if it's not 0. We're calculating the memory address within our RAM of the bitmap data. That's somewhere in our program code further down. And then we're just converting to a screen coordinate, because there's sort of 8 lines per tile. So we're multiplying the Y by 8 here. And we're showing this into the screen with a show sprite routine. We're then showing some bits of text to the screen here, just the fire message, the high score and the URL. And then here is the start of our actual game loop here. So this is the main level routine. We're waiting for fire. We do this at the start of the game or the start of a new level. Clear the screen, recenter the player, and calculate the objects for the level. This is the enemies and also the mines and the crystals and things. Here's our main loop. We store key presses in X, and we've got a loop of Y here, so we can make this higher to make the game slower or lower to make the game faster. Here we're reading in the controls, and if a key is pressed, we're storing that key press in X here for processing down here. Once we've done our delay loop, we're showing the user interface. That's the text, the score and the lives and things like that, important stuff. And then we're removing the old player object here before calculating any movements to the player. Now, if a player holds down, up, down, left or right, they will start accelerating, but we don't want that to happen too fast or they'll quickly get out of control. So there's a timeout where the key is ignored, and it's controlled by this entry key timeout here. And what we're doing is, if the key timeout is non-zero, we're skipping over all of the other directions. So this is the code that handles movement. We're loading the direction into Y here, and then we are using the player object, which is being stored in 0-page entry IX here. And if a direction is detected, we're altering that acceleration direction here, and that will move the player faster in that direction depending on what's been pressed. If the fire button's been pressed, we're using the fire bullet routine, and if we had a fire 2, we would have an instant brake option where we would immediately stop acceleration, but this system I don't believe we can do that, so we've got that disabled here. Finally here, we've got the routine to draw all the graphics back to the screen, and then we jump all the way back up to here for the next iteration of the main loop there. Very straightforward. Here's our clear screen routine. The screen is at memory address hexadecimal 4000 and it's 2000 in size, so we're just clearing the screen there. Our print character routine here is using the show sprite routine essentially. We're loading the address of our font, we're multiplying the character we want to show by 8, but we do have to subtract 32 because there's no characters before space, character 32 in our font. So we're just subtracting 32 and then multiplying that up, adding it to the address of the font. And we're taking the X and Y position and calculating those as a screen location, and then using the show sprite routine to do that work. Okay, now here's our blank sprite routine. This will take an object off the screen. First, we're checking the object's collision program. An object with a collision program over 250 is a dead or unused object, so we don't want to clear those. Otherwise, we're using the font and we're using the space in that font to clear the object off the screen. GetSpriteAddress is calculating from a sprite number the address within memory of the bitmap data. So there are 8 bytes per sprite, so we're just calculating that there. And then we are calculating the sprite frame. There's 128 bytes per bank. There's 16 sprites per bank, and there's 4 banks in total. So that is just calculating the address for the 4 frames of animation there. And then this in entirety will return the address within RAM of the bitmap data to show on the screen. Do GetSpriteObject uses 0-page IX pair here as the object address. Now these objects could be the player, the bullets, the enemies, things like that. It's taking the sprite number from IX. It's taking the X and Y position from IX, ignoring 3 bits of the Y position because basically it can't reliably show them because of the complex layout of the screen. This is just a simple bitmap routine I'm using here that can't do anything clever like that. And the X position, we can't use all of the definition that's stored within memory there, so we're just skipping 2 bits of that as well. Then here's our show sprite routine. It's getting the screen position, transferring the bytes to the screen here. This is basically the same as we saw in the simple series, so please take a look at that. And as is get screen position, I'm not going to go over that. It's all in the simple series. Here's our read controls routine. This is basically the same as we've looked at before. This one has got the joystick fire button reading routine in here, and it's converting analog to digital here, so it's a bit of a pain. I did go over this in the simple series, so again, please take a look at that if you need more detail on that. Here's the fire button routine. This is the debouncing. This is for the end of game over and the next level messages. So we wait for a fire to be pressed and then released so that we've got a clear start for our next level. While the player is not doing that, we're randomizing the random seed so that the game will be pretty random, hopefully. And then after that, we've got the font and the bitmap data. You can see there's 4 banks of bitmap data and there's the font here. Now, I actually wrote a slight modification to YQuest5 editor. The graphics were supposed to be 8x8. I'm missing 1 line, so they're actually 7x8 now. So there's 1 bit missing of the graphics, just converted them there. So these are Apple II specific here. And then finally, we've got some common routines here, which have come in from other games and things I've written. Most of them are covered in my other tutorials, and a few were taken from Yquest6502 as well, because we want to try and reuse code where we can. And that's all there is to it. That's what made up this game. And as I say, if you can make any use of this game in any capacity, you can do so. You're welcome to use it, for your fun, for your own YouTube videos, for if you can manage to sell it, good luck to you. You don't even need to give me credit. I really don't care. Anyway, though, whatever you do, I hope you enjoy your programming projects and whatever the creative works you're working on. I wish you all the best with them. I hope you've enjoyed this. Thanks for watching today, and goodbye.